Hey folks, so I'm just going to do a pretty quick video to start things off. If you want to cover this earlier in the week, that's great. I'm probably going to follow this up with one on exponent laws, kind of getting a little bit more stuff together, and we'll cover that by the end of the week. But to start things off, this is a pretty good spot. We are going to remove some examples and types of problems from this section, and if you need them in a future course coming up, I guess we kind of agreed that it would be filled in there, but it will give you a good baseline for this particular sort of question. So the first thing I want to talk about before we do talk about fractional and negative exponents and how they're related to radicals, I want to make sure that we're comfortable with a few. I'm going to list a few exponent laws, and we might not even use them all right now, but they will come up a little bit later. So in grade 9, one of the things you should have covered is if you have, for instance, 5 to the power of 3 times 5 to the power of 7. There is a way to take that and to simplify it quickly by just using a rule. So we take the two exponents, in this case that would be the 3 and the 7, and we will add them. So multiplication of two powers of the same base, so in this case the base is 5 for both of them. We can take those exponents and add them together to give us 5 to the power of 3 plus 7, which is 10. That works as long as the base is the same for any, we talked about in grade 9, whole number exponent. So 3 and 7 added for 10. Great. This works for just as a random second example. If I had base of 3, 3 to the 2, and 3 to the 5, then we would say that that's base of 3, it's the same, multiplied together, add the exponents, and we would get 3 to the 7 in that particular case. So that is sometimes called a multiplication law, and you add the exponents. There is a similar rule that we can come across as well, where instead, if we have the same base and we are dividing the two expressions, then we could say that 8 to the 5 divided by 8 to the 2, we subtract those exponents instead, so we get 8 to the 3 in this particular case. Again, taking the 5, taking the 2, subtracting those values and getting the 3. So this is a fast way to deal with some things that involve exponents. Now, if you want the long explanation as to why that actually works, in the first case, if we were just to take this and deal with it again down here, 5 to the 3 is the same as saying 5 times 5 times 5. And then we'd be multiplying it by 5 to the 7. I'm going to regret this. 5 times 5 times 5 times 5 times 5 times 5 times 5. There. 7 times. And then if I'm multiplying 5 together this many times, the brackets don't even matter anymore. So I get 5 times 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 one more 5. That's actually 10 if I count them up. And that's exactly what we got the first time too. If instead I'm looking at what happens in the case of doing the division, this would be the same thing as 8 times 8 times 8 times 8 times 8 5 times, divided by 8 times 8 2 times. When we have a fraction set up, if you have the same number in both the numerator and denominator as a factor, we can take those factors and actually cancel them out. So in this case, I can cancel out 2 of my 8's in the numerator with 2 of my 8's in the denominator. That leaves me with 3, and that's exactly the same thing as we got last time. These two rules work in any case, so they're going to be very, very helpful to us coming up. The other one that you may remember as well would be something like this. 8 squared all to the power of 4. So raising something that has an exponent in it to another exponent. In this particular case, if we did kind of the long way, if you raise something to the power of 4, you're multiplying it together with itself 4 times. So that'd be 8 squared times 8 squared times 8 squared times 8 squared. If I listed out, that'd be 8 times 8 for that first one, and then 8 times 8 for my second one, 8 times 8 for my third one, and 8 times 8 for my fourth one. This is, again, an example where the brackets don't even matter anymore. So I have 1, 2, 3, 4, 5, 6, 7, 8, 8 currently left over. So the fastest way to write that would be 8 to the power of 8. Now, the way that we can get that from the original expression is actually by multiplying those two exponents together. So our rules are going to be, if you're multiplying two exponents with the same base, then you're going to do addition of the exponents. If you multiply together two powers that have the same base, we're going to add those exponents together. If you're taking two powers that have the same base and you divide them instead, you're going to subtract the exponents. If you take a single power that's raised to an additional power, then we're going to multiply those exponents together. That's going to be helpful for what we're going to cover in just a moment. So it's from grade 9, but we're going to bring it back for this stuff. So if that's true for whole numbers, the hope would be that we're going to come up with a system that allows it to be true for fractions as well. So in the current example that I have right now, I'm taking two things. I'm going to just do the top one for now. So that is 2 to the 1/2 times 2 to the 1/2 is equal to 2 to the power of 1. So 1/2 plus 1/2 is 1 whole. So we have the same base. So if we add together the exponents, 1/2 and 1/2, we should get 1. So this should be a true statement. Now, what times itself gives you 2? Well, when you find something that multiplied by itself gives you another value, sometimes we call that thing the square root of the value that we get in the end. So we're looking for the square root of 2 when multiplied with the square root of 2 would give us 2. So we know that this would be true. And if you're unsure of that, from the last video, we talked about how, that would be the same thing as root 2 times 2, the root of 2 times 2 under a single radical, which would be the root of 4, which gives you 2. So all that is just the same thing. So really what I want to focus on is this right here. Because if 2 to the 1/2 times 2 to the 1/2 is 2, then that should mean that the square root of 2 times the square root of 2 is also equal to 2, which together means that root 2 and 2 to the 1/2 have to be the exact same value. So what we're seeing here is that the square root is the same thing as a 1/2 power on a value. So we're going to be able to use those two things interchangeably. This idea of the 1/2 power to go along with the square root. So anytime you see a value written one way or a value written the other way, they can be interchanged with each other, and that can happen anytime for any base. So the 2 is not important. You could use any value. Of course, we get into some bad things happening if you take negatives and try to do the square root of that, which we talked about earlier. So it's not just any number is allowed to have a square root taken, but anytime you can take the square root of a number, it's the same thing as saying the 1/2 power of that same value. The other one that we have here, I wrote down 7 to the 1/3 times 7 to the 1/3 times 7 to the 1/3 is equal to 7 to the 1. Again, according to that same rule that we were just discussing, if I do this, it should be the same as adding together the exponents. So if I just take the grouping of the first two values here, that would be 7 to the 1/3 plus 7 to the 1/3. Adding 1/3 and 1/3 together would give us 2/3. So in this case, 7 to the 2/3. And I still have my undealt with 7 to the 1/3 at the end of that statement. I'm going to do the exact same thing. I'm going to take I'm going to take these two things, and I'm going to use the same rule. So same base, can add together the exponents. 2/3 plus 1/3 is 3/3. And 3/3 is the same thing as saying 1. And so the stuff on the left is definitely equal to 7 to the 1, as we've shown down below, if the rule is that we're allowed to add together those fractional exponents. And we're hoping that it is. So if that was true, another way of stating that exact same problem is to say that if we're looking for something that when multiplied together 3 different times gives us 7 to the 1, which is the same thing as 7. Well, if we flip the problem around, what value multiplied by itself 3 times gives you 7? We call that the cube root. So this would be the cube root of 7 times the cube root of 7 times the cube root of 7 is equal to 7 itself. Just like last time, if we link together the idea of this thing up here and this thing down here, there's 3 of the same thing gives you 7 to the 1, which is 7. 3 of the same thing gives you 7 to the 1, which is 7. That must mean that these two things are equivalent. So 7 to the 1/3 is equal to the cube root of 7. That is how that works. And so we have a little situation where the square root is the 1/2 power. The cube root is the 1/3 power. If we extend this, it's actually true that the nth root of any constant value is the same thing as c to the 1 divided by n. So a lot of times we might forget that the square root of, for instance, 9 is the same thing as saying the square root, actually writing a 2 into the index. We never do that because it's seen as being kind of a little overkill. We assume that when the index is not written in, it is actually a square root. So the index tells you what the fraction will be if you want to write that as a fraction exponent instead. So an index of 2 is the same thing as saying a 2 in the denominator of a 1 over something, so 1 over 2. If we wanted the cube root of 64, that could be written as 64 to the 1 over 3. The fourth root of 1,000 would be equal to 1,000 to the 1/4. Now that actually doesn't go in nicely. It's a crappy number. It's an irrational number, as we've talked about before. But this is the relationship between fraction exponents and roots or radicals. Now, as I said, we're going to kind of shorten or tighten up this part. You can do something with the numerator so it's not always a 1. And if you want to look at that on your own, in the same section of the textbook that I'll get you to read along with this video and try some stuff out, if you wanted to extend it and look at the other examples in that section, then it will talk about applying both powers in the numerator position and what's going on in the denominator position and being able to write radicals that are associated with those. Now, just as a couple examples, if we were asked to evaluate numbers that have these fraction exponents in them, so we would have 81 to the 1/4 power. That's the same thing as the fourth root of 81. If we take a look at that chart that we had a while ago that has the x squared, x to the third, x to the fourth written on it, and we skim down the row that has x to the 4, and we look for the number 81, well, we're going to see 1, and then we're going to have 16, and then we're going to have 81 right away. So it gets up, the numbers grow really quickly in the x to the 4 and the x to the 5 column. So we would see that the x value of 3 would go along with x to the power of 4 being equal to 81, which means that the value of the fourth root of 81 is going to be 3, which means that the value of 81 to the 1/4 power is also 3, because the 1/4 power is equivalent to the fourth root. So 1/4 power, or a 1/4 exponent on the 81 is the same thing as the fourth root of 81. Likewise, if we take a look at the example of 9 divided by 25 to the 1/2 power, 9 divided by 25 to the 1/2 power is the same thing as the square root of 9 over 25. And we actually said that when we take a square root of a fraction, in this case, it's a nice rational number because 9 is a perfect square and 25 is a perfect square. You can take the square root of those two things separately and it means the same thing. So the square root of a fraction is the same thing as the square root of the numerator divided by the square root of the denominator. In this case, the square root of 9 is 3. And the square root of 25 is 5. So we get 3 over 5, which means that the square root of 9 over 25 is 3 over 5. Also means that 9 over 25 in a bracket to the 1/2 power is equal to 3/5. Now, this bracket is really quite needed because if we don't have that bracket there, then it's really hard to tell. I would probably assume that that was just 9 to the 1/2 and then 25 just normal plain 25. If I write the bracket there, the exponent always applies directly on whatever it's written next to. Without the bracket, as I said there, you can't really tell that the exponent is on like the fraction 9 over 25. You would probably have to assume that it's on just the 9. But in this case, the 1/2 is on the bracket. So it is a power that is applying to everything that's inside of the bracket, in this case 9 over 25. And that's why we wrote the square root around the whole 9 over 25 bit when we turned it into a square root instead. So that's how we can evaluate fractional exponents. We can either kind of recognize them as radicals or roots and then just do what we were already doing earlier in the semester. Or if you get comfortable enough with them, you might be able to just kind of recognize what it is in your head and write down the results from there. Now, negative exponents. We're going to basically just do the same thing. And we're going to talk about how if we wanted the exponent laws to stay the same, then it's really obvious what the answer should be before we even know what a negative exponent does or is. So in the case of 3 to the negative 1, we multiply that by 3 to the 2, we know that that should hopefully be equal to 3 to the 1. Why do we know that? Because if we follow the law of adding exponents when we multiply two powers like this of the same base together, so this would be 3 to the negative 1 times 3 to the positive 2 is going to be base of 3, same for both of them. We add together the exponents of negative 1, positive 2, add those together, get a positive 1. Okay, so that followed our exponent law. Now, let's figure out what that has to be for this to be true. So I'm going to just leave it as a question mark there. I'm going to turn my next piece, which is 3 squared, into 9. And so the question becomes, what is it that when I multiply it by 9 gives me 3? I could actually set this up as an equation where I'm solving for the question mark. I probably could have called it x or something, but for the time being, question mark. So question mark times 9 is equal to 3. So what if I divided that 9 on both sides of my equation? So I'd have question mark times 9 divided by 9 is equal to 3 divided by 9, because I have to divide by the same value on both sides in order for the equation to still be true. So if we take that 9, which is now a common factor in both my numerator and denominator, I can cancel it out. Left with question mark. So question mark is equal to 3 9ths, which is the same thing as 1/3. So what that means is question mark is 1/3. Now, if we take what that question mark was originally, which is 3 to the negative 1, 3 to the negative 1 is actually equal to 1/3. Now that's interesting. That probably is a little bit unexpected. You might have thought that a negative would work its way into what was going on there, but that's not true. It actually is something that we call the reciprocal instead. So if we have 3, you can think of 3 as being like a 3 over 1, and then the reciprocal is when you take the numerator and the denominator and you switch their positions. A lot of times people will call it the flip. We don't call it the inverse, even though that sounds a lot like something people use in that particular type of expression. Inverse is a really special word in math, and we don't want to confuse it for reciprocal. So this is the reciprocal, and it's taking that numerator and denominator and flipping their positions so that the numerator goes into the denominator, the denominator goes into the numerator. So 3 over 1 is what we started with. If we flip things so that the denominator goes down and the numerator goes up, we would get 1/3. That's what a -1 exponent does. So what if we were to, what if, I'm going to put another little question in here first. What if we were to look at what happens if it was a -2 as what the value of that is? Well, I do know that if I took -7 to the -2 and multiplied that by 7 to the 3, that's supposed to give me 7 to the 1. So 7 to the -2 times 7 to the 3. Now I'm going to have a little bit of regret here probably. So 7 times 7 is 49. 50 times 7 would be 350. So this is 343 is equal to 7. And again, I'm going to do the same thing we did last time. I want to get rid of that 343 on both sides of my equation. So I'll divide by 343, which leaves me with, if I reduce this, 7 it goes into the numerator and 7 goes into the denominator. Because I'm using powers of 7, that's why I can kind of do that quickly. If you can check it, 7 divided by 7 is 1. 343 divided by 7 is 49, so that reduces nicely. It also cancels out on the other side of my equation, and I'm left with 7 to the -2 is equal to 1 over 49. This is a reciprocal as well. However, it also is not the same number. So it's 7 to begin with, but it is 49 to end with. So if I take a look at that and I say, okay, well, it was a 7 to begin with, but it became a 49. So what is it that I need to do to go from 7 to 49? Well, I need to square it. Oh, that's what this is. So instead of being a 1 there, which leaves it the same, the 2 is actually squaring it. So it squares it and does the reciprocal. So what would, in this case, 5 to the -3 give us? Well, if we actually knew that it was 5 to the -3, that would be reciprocal and the cube of that. So the cube of 5 is 125. We flip it, and it gives us 1 over 125. In general, if you have some number to a -n exponent, where n could be any whole number, then it would be true that that will give you 1 over c to the power of n. So we can flip it, that's what the negative part does, and then we just apply the normal power on whatever has then flipped into the denominator. So this is also true for fractions. So if we have a fraction like 2 over 7 to the power of -2, so the negative is going to flip. So first it becomes 7 over 2, still to the power of +2, because all the negative does is do the reciprocal. It does the flip. So we would have 7 times 7 is 49, and 2 times 2 is 4. So the power of 2 is going to apply to both the numerator and the denominator. So it's 7 times 7 as well as 2 times 2. So 49 over 4. So again, negatives do flip, negatives do reciprocal, and then you apply the power that's still there to whatever's still kicking around after you've done your reciprocal. So, as a little kind of a side/interesting thing, if we know that and are feeling like that's okay or kind of comfortable, then we can discuss, what does something to the power of 0 mean? Well, power of 0, you might already know what it is, but we can show by using a negative exponent what it definitely is. So if I take something really simple, like 4 to the power of 1, and I wanted to show what 4 to the power of 0 was, Well, I can multiply that by 4 to the power of negative 1. And since I have the same base, I could add the exponents together. And so I would get positive 1 plus negative 1 is 0. And so this is definitely true because it's the same thing on both sides of my equation. So 4 to the positive 1 times 4 to the negative 1 is equal to 4 to the 0. Well, I know that 4 to the 1 is just 4. And I now know that 4 to the negative 1 is the reciprocal, which is 1/4. So 4 to the power of 0 is 4 times 1/4. Well, that is a 4 over 1 times 1 over 4. Same thing in the numerator and denominator, which means I just get a 1 at the end. Which means that 4 to the power of 0 is 1. The 4 in this example is actually not important. If I wanted to use a c there instead, I would get c to the power of 1 times c to the power of negative 1 is equal to c to the power of 0. I could go through the same steps and get that c to the power of 0 is actually equal to 1 in every single case. So if you just take any number to the power of 0, always going to be equal to 1, no matter what. So what I'd like you to do is if you could, if you have your textbook with you and you'd like to try some of the questions that I'll post along with this video, that would be really great. And I hope that you're staying safe and being well. Take care, folks, and I miss you. See ya.